Welcome back to Efficiency Solutions. This is a demonstration of our Workcell analysis, improvement, and scheduling tools. If your manufacturing processes utilize work cells or lines, you need to manage them efficiently and effectively. There are many attributes involved in cell design, layout, and planned performance. We're only going to address planned performance in this video. It's been my experience that in manufacturing, mathematical solutions are almost always the best solutions. That really applies in work cell management and improvement techniques. This is our cell performance planning tool. It's very easy to use, and it helps you perform the calculations necessary to determine the ideal number of processes, operators, and cycle times for your work cells. When using this tool, like our scheduling tools, we only enter data in the non-colored white cells. All the other cells are locked to avoid corruption of data. At the top of the screen, we enter the hourly direct labor rate in this cell. Then the number of shifts, work minutes, less breaks, and an estimated customer demand. This will calculate takt time for you. Let's say we have an existing work cell with 5 processes and 5 operators used to assemble part number ABC-1. First, we would change the -1 to -1-96 to represent the current demand for future reference purposes. Next, we would enter the number 1 in the blank cells above the process cells that we plan to use. For this example, we will be using processes A through E. We have determined that process A takes 120 seconds to complete, so we enter 120 in this cell. Process B is 180 seconds. Process C, 300 seconds. D, 60 seconds. And process E is 240 seconds to complete. Notice that process C is now red, indicating that it is the bottleneck process. And if there is any wait time, it is indicated here and will affect our work in process, throughput rate, and lead time negatively. Let's review the information we have developed so far. We see the capacities of all 5 of our processes, the bottleneck process, wait times between processes, and the total amount of work in process between each process. If this plan were implemented, we would have 10 units of work in process between processes A and B, 8 units between B and C, 45 units between processes D and E. Capacity is at 12 units per hour, and the direct labor utilization is 60%. Our 12 unit per hour capacity meets TAC or demand, and our direct labor cost per unit is $8.33 each. Now let's reduce the bottleneck time of 300 seconds by adding an additional operator at process C, reducing the bottleneck to 150 seconds. We see that work in process is reduced by 8 units between processes B and C. Capacity increases by 3 units to 15 per hour. And direct labor utilization increases from 60% to 62.5%. We are 3 units ahead of our demand or TAC, and our direct labor cost has decreased by 33 cents to $8 each. If we look here, it says minimum operators needed to meet TAC is 3.8. Let's look at only using 3 operators. First, we notice that work in process is now 0. Capacity is 12 units per hour, direct labor utilization is at 100%, and we are able to meet demand. The direct labor cost per unit has dropped from $8 each to $5 each, and we are utilizing fewer operators than originally planned. Now, because we plan on increasing demand in the future, Let's design the cell for a 20% increase in demand to 128 units per day. First, let's change the part number to ABC-128 to reference the increased capacity or demand for future reference. Well, we know that our 3 operators are currently running at the capacity rate of 15 units per hour, so we need to add at least 1 more operator to our process. Let's add that operator, and then let's look here to the ideal cycle time in seconds column. It shows 225 seconds. If we add the additional operator and rearrange the tasks between the 4 of them to 225 seconds each, we should meet the increased demand and keep the same direct labor cost. Based on this analysis, we would enter the 300-second 3-operator runtime for part number ABC-96-3 and the 225-second 4-operator part number into our routing screen and begin to schedule production. Let's simulate entering an order for 96 units. We enter the part number in this cell right here and the order quantity here. We have a shop work schedule from 7 a.m. to 3:30 p.m. with a 30-minute lunch at 12 p.m. If we schedule the job to start at 7 a.m., it should be finished at 3:30 p.m. as shown here. If we change the order quantity to 75, the scheduled finish time would change and it would end at 1:45 p.m. As demand fluctuates, we schedule production according to demand using the real-time scheduling module you reviewed here and in earlier videos, and track efficiency to quotes and routings, problem codes, overproduction, and defects on every customer order that is produced in real time. The actual in-plant line balancing processes can be difficult and time-consuming, and for those reasons alone, you need to be relatively certain of what your results will be for the resources and time used in the design and improvement processes. I hope this demonstration has successfully illustrated how our systems may help you improve yours. Thank you for visiting Efficiency Solutions.